Okay, let's start considering graphs of the sine and the cosine function. Okay, sorry everyone, I just need to fix this. Okay, so when we're considering our sine graph, as we can see here, let's start by thinking again back to where this comes from. So we looked at this in one of the earlier videos, the animation showing where sine comes from. Hopefully this is going to load. Here we go. So once again, we're just drawing sine, the blue curve here. Remember, sine is defined as being the vertical displacement obtained when a particular angle is subtended at the centre. And we can see that it's a periodic function because as it keeps going, the values increase, they're getting larger and larger until they reach 1, and then it decreases back to 0 again. And this is where our sine function is coming from. So if we're looking at our sine function here, it's drawn just between negative 2 pi and 2 pi. Remember, with our unit circle, we had one full circle. When we went around one full time, we've gone from 0 to pi to 2 pi. So this is where the values are coming. Here, we had a vertical displacement of 0. At pi on 2, we've got a vertical displacement of 1. We're getting this value here. At pi, we've got a vertical displacement of 0. 3 pi on 2, vertical displacement of negative 1, 2 pi, we're back here. We can get the same thing by going in a clockwise direction to go from 0 back to 2 pi. And this graph continues. So what is the domain? The domain is all real numbers unless it has been restricted. When you're asked to sketch these graphs, you will always be given some kind of limitation because otherwise it could keep going forever. Because it does keep going forever. There's infinitely number x intercepts as it keeps stretching into infinity, negative infinity and infinity. The range here is going from negative 1 to 1. The amplitude. The amplitude is defined as being half the distance from the peak, here's the peak, to the trough, the bottom. Half the distance from the maximum to the minimum point, okay? Amplitude is not just defined as being the distance from the x-axis to the maximum point, because my whole graph could be translated upwards, but it's defined as being half the distance between the maximum and the minimum. In this case, half the distance between the maximum and the minimum is 1. The period is how often we have one complete cycle before it starts again. Here we had one complete cycle of 2 pi, and then it went around again. So we had a complete cycle here of 2 pi. Then it will start again and we'll have the same shape repeat, and then the same shape again. It's a periodic function that repeats every 2 pi units. The cosine graph is very, very similar, as you would be aware. And our cosine graph, like we were seeing before, so again, if we just come back here for a minute and let's look at our cosine graph instead, get rid of our sine graph. So our cosine graph that we're drawing here, the red graph here, we're again measuring the distance, the horizontal displacement in this case, from the y-axis, and we can see this happening here. One thing I do want you to notice when you're looking at these two graphs is that they're very, very similar. To get from a sine graph to a cosine graph, it's just a simple horizontal translation. It is, in effect, the same graph, just that it has been translated. So if we go back to what we were looking at here, sorry, I've lost my place just now. So if we're looking back here again at our cosine graph, this one, in this case, starts at 0, 1, which makes sense because, again, if we think about our unit circle, cosine is defined as being the horizontal translation. Here, where the value of theta is 0, we get a horizontal displacement of 1, so it starts at 1. At pi on 2, the horizontal displacement is 0, which is why it's here. At pi, we've got an x value of negative 1. At 3 pi on 2, an x value of 0. And at 2 pi, a value of 1 again. So this is where this graph is coming from. Once again, the domain is the reals. The range in this case is from -1 to 1. amplitude again is defined as half the distance from the maximum to the minimum, which in this case is 1, and the period, it repeats every 2 pi. It's repeated, then it will repeat again, and so on. Alright, let's look at sketching some specific functions. Let's think about transformations actually first. Here's a general equation of the sine function. It would be exactly the same for the cosine function, okay? This would be the same as if we had cos there. We think about our translations. We've done so many transformations now. The effect of the positive or negative part here, that tells us if it's been reflected across, if it's in front there, it's reflecting across the x-axis because it's affecting the y values. The effect of the a value here, when the a is in front of the equation, in front of the basic function, it affects the y values, which means it has been dilated by a from the y-axis, okay? And when we dilate by a from the y-axis, we stretch it this way, which means we affect the amplitude. The effect of the n here that we've got, this is within the function, it's with the x. It affects the x values, which means it stretches this way, which means it is dilated by 1 over n from the x-axis. And when it's stretching it that way, it's affecting the period. And the period of a function is always equal to 2 pi, which is what it is for our basic function, divided by n, because we're multiplying it by 1 on n. If our x, I don't have it written here, but if our x was positive or negative, so our x here could also be positive or negative. So that again, we're getting reflections, but in this case it would be reflected across the y-axis, as it would be affecting our x values. We then have our negative b and our plus c. And I'm sorry, I'm kind of running out of space here. Our negative b, when it's within there, it's affecting the x values. So we are translating by b units in the positive x direction. And our c here at the end, because it's separate from the function, it affects the y-axis, so we have translated by c units in the positive y direction. These transformations should be nothing new. It's very similar to what we've done for every other function so far. We're just now performing them on our circular functions. Today, we're just going to consider the effect of dilations and reflections. We're going to leave translations for another time. So let's have a look at what some of these graphs will look like when we need to sketch them. As I said, you will always be told how much to sketch because we don't want to sketch to infinity. Here we want to sketch the graph of y equals 3 sine 4x for one complete cycle, for one period. In this case, they don't care what the domain is, just saying that you need to see one complete cycle. Let's think about the transformations. The 3 here means that it has been dilated by 3. It affects the y values, so dilated by 3 from the x-axis, which tells us that the amplitude, the amplitude of my graph will be 3. The 4 here, it's with the x, which means it affects the y values, so affects the y value, it's with the x, so it's affecting the x values, which means it's been stretching this way. So it's dilated by 1 on 4 from the y-axis. And our period then we can figure out by taking 2 pi over 4, which means our period will be pi over 2. When you do one complete cycle, it's up to you where you measure it from. The easiest thing is probably to go from 0 to the end of our period. So if we draw our graph, label x, y, it hasn't been translated, so that means it's going to start at 0, 0, as do all sine functions unless they've been translated. The period this time, so the amplitude is going from 3 to negative 3. Our period is pi on 2. Now, I find it easiest if you can plot out your 5 main points. It makes it so much easier to sketch this. So we're thinking about what's happening. Normally, when we went around our unit circle, thinking about our sine graph, we had what happened at 0, pi on 2, pi, 3 pi on 2, 2 pi. And that's where we're getting the values of sine having 0, 1, 0, negative 1, 0. We can get the same values for this graph, but it's just been dilated. So that means instead of getting to pi on 2, or one complete cycle by 2 pi, we've got one complete cycle happening by pi on 2. Which means we'll get halfway around at pi on 4. We'll get a quarter of the way around at pi on 8, because I'm dividing it by 2. So I've got pi on 8. This is the same as 2 pi on 8. This would be 3 pi on 8. And then I have pi on 2. Our basic sine graph, when it hasn't been translated, starts at 0. Remember here we had our value of sine of 0, 1, 0. 0, then 1, but in this case it's been dilated by 3. So my maximum point will be here. I then have another 0 halfway around, I get back to a 0 value again. 3/4 of the way, and it's the negative value. And then at the end, I'm back to where I started at 0. I can now connect my points together like a dot to dot. Make sure that you're drawing one smooth curve. This is my graph. I've got one cycle. We can label the key points. So this is the point pi on 8, 3. This is the point pi on 4, 0. 3 pi on 8, negative 3. Pi on 2, 0. And starting at 0, 0. Just be careful when you sketch. Make sure it looks symmetrical. We don't want to see sine graphs that look something like this. Okay, that's not symmetrical, that's not a periodic function. It needs to be symmetrical. Okay. So let's now have a look at a slightly more complex function that we're sketching. So we're sketching this graph of f given here. We've got a domain this time from 0 to 6. Because it is negative, that means it's been reflected. Okay? So our normal cos graph starts at 1 and goes like so. Our reflected cos graph then will be the opposite. It will start at negative 1. Okay, so this is our reflected graph. Half. It's been dilated by half from the x-axis. So the amplitude is half. Pi on 2t here, this means that it's been dilated by 1 over pi on 2 from the y-axis. Period we determine by saying 2 pi over whatever the argument is, whatever's here with the x or the t in this case. 2 pi over pi on 2. If we're trying to figure out what this means, that's the same as saying 2 pi divided by pi on 2. Over means the same as divided. If I'm dividing by a fraction, what I do is I change it to a times and I flip my fraction over. 2 pi is over 1 when it's not written. I can cancel out. 2 into 2 cancels out. So I've got a period of 4. Okay, so we can start sketching. We're sketching between 0 and 6, but our period is 4. This time we've got t on this axis because we've got a t given there. Oh, sorry, that should have been a t in there, shouldn't it? So we've got a t and our f or our y. Let's call it y. So we're going from 0 to 6, but our period is 4. That means we'll start here at 0. At 4, we're going to get one complete cycle. So if we're dividing this into 4 sections, we half it to get 2, quarter, 3/4. and then it's going to keep going, so we're going to have an extra half of the cycle. But to get to 4, that's where we're going to get 1 complete period. Our amplitude is half, so it's just between half and negative half. Remember that we are starting, it's a reflected graph, so we're starting in the negative section. So my first point is here at negative half. Then our cos graph goes to 0, so we get our main points, our 5 main points within our cycle, because our first cycle finishes at the end of 4, that's 1 period. At 2, we reach our maximum, so we have our minimum, x-intercept, maximum, x-intercept, minimum, x-intercept, maximum, and we've continued to the end of our domain. So think about, always start by dividing up your x-axis so you can plot your main points to make sure it's going to look symmetrical, to make sure that you have all of your key features. Now we can sketch it like a dot to dot. Make sure it's using one smooth curve. Make sure, I think that my scale went a bit wonky, but make sure that it's actually curving here, we're not using straight lines. We've got a given domain, I need to clearly give coloured in circles for my endpoints. I can label all key features like I did before. And we've got our graph. Notice that it does give us 1.5 lots of the cycle here. One complete cycle is between 0 and 4, which makes sense because that was our period. Then we've got another half of the cycle because we've got another half of the distance. Period is 4, so half the period would be 2, so we've got another half of the distance there. Sketching, you need to make sure that you've got a reasonable scale, you need to make sure you're using a smooth curve, you need to make sure you're labelling all key features. You need to make sure that you're labelling your axes with the variables that were given in the question. The last thing that we can talk about for this particular exercise is how to find new functions given a list of transformations. And again, this is something that you've done time and time again so far. So find the equation of the image y equals sine x under a dilation of factor 2 from the x-axis. I've said it before, I will say it again. Use mapping. So much easier to get it right. A dilation of factor 2 from the x-axis. Here's the x-axis, from there is stretching this way, it's affecting the y values, so we get 2y. Followed by a dilation of 1/3 from the y-axis. From the y-axis stretches this way, so that means it's affecting the x values. So, therefore, we get 1/3 x equals nu x. That means that old x equals 3 times nu x. 2y equals nu y. That means that y equals nu y over 2. We can substitute this into our equation. Our original equation was y equals sine of x. When I substitute in, I get nu y over 2 equals sine of 3 of nu x. Therefore, y equals 2 lots of sine of 3x, and we have our new equation. This mapping stuff is not new. We've done it quite a lot before, but again, I'll reiterate, please use the mapping process.